Hey everybody, and welcome back to Algebra 2 Online. So the goal for today is to talk about a very important characteristic of a quadratic, and that is something called the discriminant. So I've got the definition up here. So it's really just the part of the quadratic formula that is under the square root. So this part over here, b squared minus 4ac. And it's important because it tells us something about the number and nature of the roots, and nature meaning like real or unreal roots. So the three cases are here, and I always approach this just with like an intuitive kind of graphical understanding of what this stuff would mean. So if b squared minus 4ac is less than 0, right, we know that we're going to get imaginary roots. We're going to get something like, the quadratic could look like that. And you always will get two imaginary roots because you're going to do plus or minus the square root of like something I, but it can't be 0 because that's this case down here. So we specifically are getting plus or minus two different numbers. So we're going to always, in this case, get two imaginary roots. So it tells us, we get two different roots, and the nature is imaginary. This is kind of what they look like, those kind of cases. You can also have it like that, right? Actually, my OCD, I want this to be blue. So you could also have b squared minus 4ac equals 0. And in that case, you're going to kill off the whole square root part here, and you literally have just the quadratic formula, the x equals negative b over 2a part is all that's left over. So this really is the roots. And the s is kind of weird there because it's one of those where you really only have one unique number. You have basically a case like this, where the root sits on the x-axis, and the root is just literally like the line of symmetry, the negative b over 2a part. So technically it's still 2, but a lot of times we say just one repeated, and it's a real root. It's one that you can actually see the x-intercept there. You can see it on the x-intercept. And then the other case is kind of your case you're most used to, I would say. So if you have this part, b squared minus 4ac, being greater than 0, then, you get stuff like this, maybe, where you get just two different real roots, right? You get plus or minus two different numbers there, and then you end up with this root and this root. So in this case, you get two different real roots. So just by looking at that, we can literally determine tons of stuff about this quadratic. We can determine the number of roots, whether we get two different ones, distinct roots, or one repeated root. We can determine the nature, whether they're imaginary or, in these two cases, real. We could also figure out what the graph kind of looks like. Would it be something like this or this, which floats above the x-axis or below? Would it be one where it just touches the x-axis? Or is it one like this where it crosses in two different spots? So we're just going to use this today to do some kind of challenging kind of questions related to the discriminant. And they end up being a lot of quadratic inequalities here, because if you look at this case and that case, right, this truly is a quadratic, right? b squared minus 4ac greater than 0. The squared part is related, this whole thing needs to be greater than 0. That's a quadratic inequality. So the reason I talk about the discriminant after quadratic inequalities is because today there's going to be some problems you need to know stuff about quadratic inequalities for. All right, so for this first problem, it just says x squared plus 3px plus p equals 0. And this thing has one real root, and p is a non-zero constant. Find p, okay? So, just from what I just said with the one real root, that means that basically b squared minus 4ac, the discriminant, has to be 0. It's basically just taking x equals negative b plus or minus the square root of blah, 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 all over 2a. This part is 0 because then this whole thing just reduces to negative b over 2a. Like, that's going to be what the root is, right? Basically, we have this quadratic, and we should just identify what A, B, and C are. From here, if I bring this down, we can see that A is 1, right? B is 3 times whatever P is, and C is just P, right? The B is always just the thing in front of X, A is the thing in front of X squared, and C is always the number at the end. And since P is a non-zero constant, that's just the C value. So we should have enough stuff then to just go plug things in. So B is 3P, A is just 1, C is P. And if we just go set that thing equal to 0, we should be able to find P. So we get 9P squared minus 4P. I would just factor out a P. It's the easiest way to solve this thing. Then, basically the two roots would be 0 would work, right? And here, if you just add 4 and divide by 9, P could also be 4/9, right? So these two things are what it seems like P could be, but you got to be careful. It says P is a non-zero constant for whatever good reason. So that means that this one needs to get thrown out. And so my only solution is just 4/9. That's the only thing P can be. All right, so let's just do another one. It's kind of similar but different. We've got a different quadratic this time. K is a positive real constant. And the first thing I want you to just do is find the discriminant. So the discriminant is just the b squared minus 4ac part, right? And again, just identifying up here, right? We see that a is 1, like the last problem. B is k plus 3. It's just the thing in front of x. And then c is k, right? So if we just plug things in, we get k plus 3. All of that squared is b squared, right? Then minus 4 times a times c, which is k. And then if you just go and multiply all this out, you would get k squared plus 6k plus 9 from the k plus 3 squared. And then you have a minus 4k, right? And so if you just simplify that a little bit, you get k squared plus 2k, plus 9. So that is my discriminant, all right? And then the second question down here says, are there values of k where f has imaginary roots? Okay. Imaginary roots means that the discriminant, which we found up here, needs to be less than 0, right? It's just the first case right here. So when this part underneath is negative, that's when we get our imaginary numbers. So we just basically need to set k squared plus 2k plus 9 less than 0, all right? And less than 0. And so really, the way that we solve this is just a quadratic inequality, right? Like the last few days we've been working on those. We need to graph this thing and get a sense of when it's less than 0, right? So the first step when you do quadratic inequalities is find the roots. And then we're going to make the rough sketch, and then we are going to answer it from there. That's kind of like the idea with quadratic inequalities. So I am going to do, this is kind of weird because we're doing like quadratic formula inside of a quadratic formula problem, but I need to find the roots of that discriminant, which was a quadratic. So I have to use the quadratic formula. K will be negative 2b, right? Plus or minus b squared minus 4ac all over 2a. And if you solve that thing out, you will notice in here, right, 4 minus 36, that's a negative number. I don't even care what negative number, it doesn't matter. So the roots are imaginary, right? So we have some sort of quadratic that's doing something like this, where it's sitting above the x-axis, because it's got imaginary roots, this thing I'm talking about. But we wanted to know, when is it less than 0, right? And, here's my here's my 0, right? So when is this thing less than 0? That's like the question, when is it less than 0, right? And never. So the question, are there values of k where f has imaginary roots? No, you don't have any values of k that do that. This discriminant would never have imaginary roots, no matter what k values you plug in. No real k values, at least, would work. Maybe I should add that little part. So no real k values. And since k is a positive real constant, there's none that work. All right, I just want to do one more of these because I know they can be kind of tricky when you first see them. So I want you to find all values of k such that x squared plus k minus 3 times x equals minus 3 plus 2k, where k is a constant, and this quadratic has two distinct real roots. So two distinct real roots is kind of the case that most people are familiar with, b squared minus 4ac being greater than 0. And it's just one of these, again, where we want to identify a, b, and c, and then we're basically going to just solve this thing out, and we'll have our answer. So I'm going to start and just kind of write this in a form where we can see what the A, B, and C is. So basically I'm just moving this part over is all I really did. So right here, A is 1, right? B is k minus 3. And this thing, k is a constant, so 3 minus 2k is going to be a constant. So that whole thing is just C. So then I just go to, my b squared minus 4ac over here, and I'm just going to plug everything in. And then got to crank through a bunch of this algebra, so we're going to have to square this thing, which we would get k squared minus 6k plus 9. And then if you just distribute negative 4, right, the 1 really doesn't do anything there, you get minus 12 plus 8k. And then combining like terms here, right, we get k squared plus 2k minus 3. And we want to basically set that greater than 0, right? This is actually a nice one. If you think like what multiplies to negative 3 and adds to 2, you would get 3 and negative 1, right? So that's my quadratic. And this is nice because I can see the roots right now are just the opposites of these numbers, right? The connection again just between roots and factors. So we know that, if I do my like rough sketch now, we got a root at negative 3, a root at 1. We know it's a positive quadratic, so it's doing something like that. And so now we can look at it and we can answer the question. We can say, when does that thing, when is it, we want specifically greater than 0, right? And so we want to describe that chunk and that chunk. And the answers then would be you have to be less than -3, or you can be bigger than 1. And that would do it. That would be the k-values that make this thing have 2 distinct real roots.